Okay, so this question is very different from the previous question because of the axis. The y-axis is now currently what? V, speed. Okay, the y-axis is speed. It's different from the previous question where the y-axis is distance. Okay, so what's the gradient of a speed coming up? What does that represent?
Whether something is accelerating, decelerating in a uniform fashion.
The gradient represents acceleration. Okay, whether it's accelerating or decelerating,
Okay.
or whether there's any acceleration at all to begin with. Okay, so we need to use this concept. If the gradient is increasing, what does that mean?
If the gradient is increasing, therefore steeper,
Yes.
that means there is more acceleration in a given period.
Yeah, that would mean increasing acceleration. So the acceleration is non-uniform.
Yeah.
Okay.
Or the gradient can just be very steep. Right?
The gradient can be very steep.
Uh-huh.
Yeah, you can have a very steep gradient.
Yeah, that means somebody freaking floored it in this.
But if you notice that the gradient is increasing, that means that there will be increasing acceleration. Okay. If you notice a zero gradient, what about a flat line?
Well, where's
no gradient? What does that mean?
It's not moving. I was moving at a uniform speed.
I have moving at a uniform speed. Any other possible answers?
Depending on where the flat line is, if the flat line's like right up against the t-axis, that means there is no movement at all.
Yeah. So if that's a good point to bring up. If you see a line that is flat like that, so the v is 0, and the acceleration, of course, will be 0. Okay, so no gradient would mean, in general, no acceleration. Okay. What about decreasing gradient?
That means that there is retardation.
Decreasing the speed.
Well, retardation.
Yeah.
So that's I wouldn't say it's a retardation. We will use this example to discuss about it later on, but generally a decreasing gradient would mean a decreasing acceleration. And I'll explain to you what's the difference between a retardation and the decreasing acceleration. Because if you look at the diagram, the graph, there's 1, 2, and 3, and 4. One of them is a retardation, and the other one is a decreasing acceleration.
Which one is which?
Since we are talking about that now, why don't you guys take a guess and tell me? Okay, so to summarize, I want you to tell me what represents a decreasing acceleration in the graph and what represents a retardation.
I think I know what it is, and it makes a lot of sense to me now.
All right, Samuel, go ahead.
2 is decreasing acceleration.
Very good.
4 is retardation, which makes me believe that the difference between decreasing acceleration and retardation is that retardation is when you are going from a constant speed and decreasing decreasing in speed, be it uniform or otherwise. Whereas decreasing in acceleration is as it is when you are slowing down the acceleration, but not decreasing your speed.
That's a good point. Just to add on, you don't have to be starting from a constant speed and then you retard. Okay, it doesn't have to be from a constant speed and you retard. You could be going up with an increasing acceleration, and suddenly you're like, hey, I gotta jam my brake. I gotta slow down straight away. So you just make a step hard on the brake, and then you really slow down.
That's retardation.
That is also retardation. So you don't have to start from a constant speed or constant velocity.
Sorry. So retardation is when the speed is when it's deceleration that starts at its highest speed now, whereas
retardation in general
uh-huh.
means that the speed decreases.
Okay.
In general, it means that you're slowing down. So it doesn't matter you're slowing down from a constant velocity, constant speed. You just slow down. So long you slow down, that's retardation.
But whereas acceleration is you're still accelerating but at a slower rate.
Yeah.
Okay, that makes a lot of sense.
Okay, so now we have some answers here. Let's fill in the rest. I. What is I? Describe the motion object in I.
Moving on a non-uniform increasing speed.
Non-uniform speed increasing.
Non-uniform increasing speed. Yeah. Your keyword is
Acceleration.
it feels like there's like a mismatch of keywords. So you gotta be careful, just be cautious about that. Okay, so let me explain to you what's if you want to talk about speed, that's if you want to use speed to talk about it, I will encourage you to use the word rate of change in speed.
Okay, so I'm just gonna put acceleration.
Or you can say rate of increase in speed. Okay. So you can see here actually generally it's best to use the word acceleration. That would be a safer keyword to use.
Okay.
You can see the gradient is increasing, so we have increasing acceleration. So it will be increasing. So I'm going to use the up arrow, increasing rate of increase in speed. That means the increase in speed is increasing at an increasing rate. It sounds very confusing, but basically what it means is that every moment your increase in speed is greater. For every moment in time, your speed is increasing at a greater rate. I hope that captures your understanding. So increasing rate of increase in speed, that would be one way of using it. If you want to use the rate of change in speed, or you want to use speed as a keyword, or you can just say increasing acceleration. Yeah, you could use that as well. That will be safer. Okay, so part 2 will be, as what I mentioned, decreasing acceleration or decreasing rate of increase in speed. Okay, so this changes the concepts a bit. Now, the rate of increase in speed, you're still increasing in speed, okay, but at a decreasing rate. Yeah. The third one, quite straightforward, will be constant speed.
Can I put no change in speed?
I would say uniform speed better. Usually the keywords I'm using is constant or uniform.
So I put moving at uniform speed.
Yeah, moving at uniform speed is fine. No acceleration. No acceleration. Okay, so the last one is retardation, but we also need to mention what's the rate. So if you notice here, the gradient is decreasing. So it's actually a decreasing retardation.
Decreasing or increasing?
Decreasing.
Decreasing retardation.
Yeah, because the gradient gets gentler as you go down to b equals to 0.
Okay, so can I just put non-uniform retardation?
No, you cannot.
Okay.
You have to put decreasing.
So non-uniform decreasing retardation.
Yeah, or you can just say decreasing deceleration.
Because I put non-uniform deceleration to full stop.
Yeah, so here's the thing. If you put non-uniform, right, it can be increasing or decreasing. So you've got to specify it.
So I put non-uniform deceleration.
Non-uniform decreasing deceleration.
Deceleration.
Or you could just put decreasing deceleration. Because when you
So it
indicate
can be increasing or decreasing deceleration.
okay, how would, to answer the question, you can ask yourself, how would increasing deceleration look like?
So decelerating faster.
Yeah, so it will look like this. I'll indicate it with a red color ink. An increasing deceleration will look something like that.
Yeah.
Okay, look at the screen.
Yeah.
This will be an increasing deceleration. Now, this is a scenario where, as I mentioned just now, maybe you're driving a car and you see a deer at night, and you're like, oh shit, I gotta jam the brake because deer don't exist in Singapore. I don't know why I say that, but that's a very good example.
So you just set a bad road.
Yeah. So if I jam the brake, this is the profile. This is the profile of what we're looking at. Because you want to have a huge force to slow down your car. Okay, when you are really jumping down the brake on the brakes, this is what's happening. And you jump forward and slow down. So this red line, you will get it when let's say the driver is stopping abruptly. Okay, the blue line, the blue curve is what you get when the vehicle is stopping normally, like at the traffic light.
Like me pressing on the brakes.
Exactly. So you will press more at the beginning to slow down the vehicle, but when you're reaching a traffic light, you'll be likely tapping it. To give it, to make sure your passengers don't puke in the car.
Don't worry, I've been there, except I didn't puke.
Okay, so in a manner of saying, an increasing retardation is when you will puke. If you're in a car, if you're experiencing increasing retardation.
It's like a sudden stop.
Yeah.
Oh.
Yeah.
So the more retardation I have, the more likely I'm gonna puke.
The sharper the
Faster, yes.
yeah. So example,
Mm-hmm.
let's use the green line. So this is something that would be very gentle for you. Example is something like that. Very gentle.
Yeah.
So you're taking your time to slow down, like, oh, I'm cruising along, relaxing. And if the bus driver does this, you'll be fine. You can read your book on the bus. You can look at the things. You can play computer games on the mobile phone. Computer games on mobile. You can play a mobile phone games on the bus, and you'll be fine. Okay, but if the bus does this, example, like a sharp
slam.
change. Yeah, you're gonna like slam into the seat. And the bus does this for every traffic light.
I wanna jump off.
We all know how many traffic lights are there in Singapore. So
yeah,
it's just gonna
the bus is gonna riot, I swear.
Alright. So I hope by explaining these different types of shapes and relating them to your daily lives, like how you take the bus, because everyone takes the bus, right?
Yeah.
You take the bus? You take the bus?
Yeah.
Yeah. Oh, by the way, MRT deceleration is usually quite standard because there's no
It's
driver.
computer operated nowadays.
It's automated. So you don't feel that.
Unless it like breaks down in the middle of the track.
Yeah.
Not to that extent though, it'll just stall out.
So that's why you don't get car sick on the train, but you can get bus sick.
On a bus.
Yeah.
But then it's called bus sick.
It's bus sick on a bus train. Now why is it car sick on the train?
I have no idea.
It's called motion sickness.
Motion sickness.
Motion sickness, that's right.
Oh,
Thank goodness it is not an English class.
yes, you would have lost your job.
Now I gotta delete that video, that part.
Oh.
To Samuel. Okay. And we're done for this.
Okay.